Now let's have another example. Example 2. So let's examine first what kind of stages we have. So we have here the input stage. Then we have another stage here. Which has input as its base and output as its collector. So this is a common emitter stage. So stage 1 here is a common emitter stage. Here is another stage. And this stage has an input as its base, but the output is at its emitter. So this is a common collector. So stage 2 is a common collector amplifier. Then you have the output. And basically, as you see here, our load is very small. It's 50 ohms. And you know, common emitter has very high output resistance, RC, which is in that case 6.8 kilo ohms. So it's much, much, much higher than the RL. So if we just connect RL to the common emitter stage, we will not see any amplification, as we will see later. That's why we put this common collector in between. So let's analyze the circuit again and see what kind of advantage we got. So number 1 again is a DC analysis. So in DC, we just cancel all the capacitors. Okay, all the capacitors will be open circuit. So let's do that. Let's apply this. So if we do this, the input stage will be removed. The output load will be also removed. And these two circuits will be just isolated because they are connected using capacitor, and the capacitor now is open. So it's like you have an open between. So they are not connected. So let's draw them without the capacitors. So this is stage 1. Has the same analysis as the previous example. There is no change at all. Okay, same R1, same R2, same beta, same RC, and same RC, same RE. So again, we will have IB equal to 5.11 microamperes, IC equal to IE, approximately equal to, how much? Uh, 0.516 milliamperes, and again VC will be equal to 5.52 volts, and VB still the same, 2.71 volt, and R by, of course, is the same, equal to, let's call it R by 1 now, 489 kilo ohms. But how about the second stage? The second stage by Thevenin will be something like this. And if you do Thevenin, you will find that R7 and V7 are exactly equal to the values that we got in the previous example. So nothing new here. So R7 and V7 both have same values from Previous example. That's not previous at all. Previous example. That's why IB and IE will be the same and IC also will be the same. So that will lead that IB again equal to 511 microampere and IE equal to IC equal to 0.516 milliamperes. And since IB is equal IB2 or the transistor is equal to IB for transistor 1, so RB R by 2 is equal to R by 1 equal to R by equal to 489 kilo ohms. But the difference here is that VC now is 9 volt, not 5 volt. But VB is still the same. But we're still in active region. Okay. Good. So let's now go to the EC circuit. EC equivalent circuit. So number 2. So let's have a line here. The AC analysis. So base 1, emitter 1, I'm sorry, collector 1, and emitter 1. Then base 2, collector 2, and emitter 2. And here is R by and also R bar. Here is IB1, here is IB2. Okay, let's continue the rest of the circuit. So, of course, in AC, the capacitors will be short. So, RE1 will be just removed, but RE2 will not be removed. RE2 will be still there and parallel with RL. This guy will be shorted, it will be grounded, the VCC, I mean, and we connect the two stages together now in EC. Okay, here is the base 1. Between the base and the ground, we have R1 and we have R2. So we will have R1 parallel R2. So R1 parallel R2. Then we will have R signal and V signal. And emitter 1, since this is shorted, so RE will be also shorted to ground. So emitter 1 is connected to ground. Here is beta IB2. How about collector 1? So if we look here, collector 1 now is connected to base 2. Like this. Now let's go now to the second and before this, and also is between the collector 1 and the ground there is RC. This is the last thing in that stage. Now let's go to the second transistor, second circuit, I'm sorry. So between base 2 and the ground, we have R2 and we have R1. R1 parallel R2. And that's it. The collector is connected to ground. And between the emitter and the ground, there is RL and RE in parallel. So here is the emitter, we'll have here RL, RE in parallel. And before we now we finished. Before we continue, just mark where is V input 1, V input 2, and also. So this is V input 1, which happens to be the same input of the circuit. So V input 1 is actually equal to the input of the whole circuit. V output 1 is here, which happens to be the same as V input 2. And VO2 here, which happens to be the same as VO of the circuit. Good. Let's draw a line. So number 1, our input. If you look between these two terminals, our input is easy, R1 parallel R2 parallel R bar. I'm sorry, here is this is IP1, not IP2. This is IP1, and here is, I'm sorry, I forgot to draw IP2, beta IP2. Yeah. Okay, number 2, let's do now the AVs. So AV1 equal to V output 1 over V input 1. And it will be very complicated to do it because you have many resistances, you have many, currents and stuff. So a good way to do that is to determine R input 2. Remember, if we look between these two terminals here, we find R input 2. So that means we can replace all that portion of the circuit and put R input 2 instead of it. So let's calculate R input 2. This will make our analysis very easy. So we will look between these two terminals, as I said. So just ignore the rest of the circuit and just focus on that part. So we're gonna draw it again. Beta IB2 R by RL RE R1 parallel R2, and let's assume there is, a source Vx produces a current called Ix, and R input 2 is equal to Vx over Ix. Remember, I am doing R input 2 not because I want to do R input 2. I'm doing that to facilitate the analysis to get EV1, the amplification of the first stage. Okay? So we can say that R input 2 equal to R1 parallel R2 parallel the resistance seen from these two terminals. Let's call it R input dash between this one and the ground. So this R input dash is equal to the voltage between these two terminals, this terminal and the ground. Okay, which is Vx over that current, which is IB2. So from that loop here, Vx is IB2. Let's do it in another. Vx is IB2 R by plus the voltage across RL or RE, or the voltage across the parallel combination. Remember, the parallel combination has a current which is IB2 plus beta IB2. So beta plus 1 IB2 multiplied by RE parallel RL. So Rn dash equal to Vx is IB2 R by plus IB2 beta plus 1 RE parallel RL over IB2. IB2 will go away. So Rn2 equal to R1 parallel R2, and finally parallel R input dash, which is R by plus beta plus 1 RL parallel RE. Nice. Now we can remove all the second stage and just put our input in our input 2 is to fit. So the circuit will be in that way here. Our input 2, which already calculated. RC beta IB1 R by R1 parallel R2 V signal R signal, and here is V input 1, and here is VO1. Now it become a lot easier, because now VO1 is basically this current, which is beta IB minus beta IB, because it's flowing from down up in the parallel combination of RC and R input 2. And V input 1 is just the voltage across R by, which is IB1 R by. I'm sorry, this is IB1. I always make it 2 IB1. IB1 R by. So based on that, if we go to another page, so now AV 1 equal to, so VO1 is minus beta IB1 RC parallel R input 2, which is a very big resistance, over IB1 R by. So this will go with this. So we end up with this very long equation, minus beta RC parallel, and R input 2 is R1 parallel R2. What else? It's very long. Yeah, parallel R by plus beta plus 1 R E parallel RL. Okay, over R bar. That's why if you do it with the same circuit without compensating the second stage with its input resistance, it will be very complicated. But with this trick, we solve it easily. So this is AV1. And by the way, everything here is known. So you can calculate AV1. AV1 will be minus what's this one? Sorry. Minus 73.21. Okay. Number 2. AV2. AV2 is VO2 over V input 2. And that's a lot easier. So let's go back and copy and paste the circuit that we have. You can just go with the original circuit. No problem with that. So VO2 is equal to the voltage across RE or RL or the parallel combination of them. And what is the current that's flowing in the parallel combination is this current, which is the addition of that current, which is IB2, and the addition of that current, which is beta IB2. So it's actually beta plus 1 IB2 multiplied by RE parallel RL. And the V input 2 is the voltage across R1 parallel R2 or from that point to ground, which is that voltage, the voltage of R by and VO2. So V input 2 is actually equal to IB2 R by plus VO2, which is beta 1. Let's do it in another case. Beta 1 IB2 RE parallel RL. So AV2 equal to VO2, which is IB2 R by, I'm sorry, VO2 is beta plus 1 IB2 RE parallel RL over IB2 R by plus, same as the numerator, beta plus 1 IB2 RE parallel RL. IB2 will go away, so this will end up with beta plus 1 RE parallel RL over R by plus beta plus 1 RE parallel RL. If we compensate now, because everything here is known, this will be it's like I didn't do the math here. Yeah, 0.51. So it's less than 1. And we know that for common collector, the best case for the voltage gain is 1. That is the best case. If our load is equal to infinity. But our load here is not infinity at all. Our load here is very small. So remember, RE here is 3.9 kilo. And RL is just 50 ohms, which is 0.05 kilo ohms. It's very small. That's why it's half, not close to 1. till this moment we can't see, you know, advantage, okay, but we will prove it now. So number 3, the overall gain, EV. Again, EV is equal to VO2 or VO over V input. VO is actually VO2, this is the second stage output, and V is actually the first stage input, V input 1. Then we can multiply by V input 2 over V input 2. We didn't do anything, so VO2 over VN2. We didn't do anything. VN2 over VN1. But we know that VN2 is actually equal to VO1. This is equal to VO2 over VN2 multiplied by VO1 over VN1. This is AV2. This is again AV1. So again, if you have any cascaded stages, AV is equal to the gain of the first stage multiplied by the gain of the second stage multiplied by the gain of the third stage, and so on. So AV equal to, we can just multiply the two numbers, 0.51 multiplied by minus 73.21. This will give us minus 17.065. Or again, approximately minus 17. Number 4, GV. GV is equal to AV, Rn over Rn plus R signal. That's very straightforward. I'm sorry, AV is EV total is minus 37.19. Yeah. And GV is minus, this is the one that's minus 17.064. Okay? But now, what is the advantage? What the common collector added to us in that circuit? Till this moment, it just complicates the analysis. So let's, remove the common collector and just hook, because again, common collector reduces the gain. So when we add the common collector, we multiply the common collector added a gain of half. Okay, so let's remove it. Let's see what's gonna happen. So let's have a set line here. The situation. With no common collector stage. So if we did this, we will have this. We will have the following. We will have the circuit, the common emitter, same circuit, and the output is just connected directly to the load of 50 ohms. Okay. The DC of the first stage will not change, so we have same R by, same IB, same IC. But let's now check what will be the gain. So this will be a very straightforward AC smooth signal model. Let's draw it very quick. RC, RL, here is VO, eta IB. Now there is no one because just one stage, and R1 parallel R2, R signal and V signal. If we do the math here, AV will be equal to minus beta RC parallel RL over R bar equal minus 100, 5 kilo ohms, 5 kilo parallel 0.05 over 489 kilo equal 5 parallel 0.05 is approximately 0.05. You can verify it yourself. It's easy. Over 489. So this is equal to minus 5 over 489. This is minus 1,022. So it's approximately 1. So you, because the load is very small, extremely small compared to our output of the circuit, which is RC. That's why the parallel combination between RC and RL, you know, goes to RL, which is small, so the EV become also small. And the situation become worse when we do GV. So GV is equal to AV, our input, over our input plus our signal. So minus 1.22 424 over 424 plus 5. This is approximately half. So this will be minus 0.4689. So it's even worse. So with no common collector, if we just connect the load to our circuit, to our common emitter, I mean, we will get attenuation, not amplification. But the common collector, although it has common voltage gain less than 1, it was have in that case, but it isolates this very small load from our common collector stage. So the gain would still hold larger than 1. It was 17. Of course, that's much better than half. Okay, guys. So again, when we do multi-staging amplifiers, we do that for a purpose. The purpose is to enhance the characteristics of the amplification, either AV, our input, or our output. Okay. Still, there is one example that I want to do with you, but it will be a homework, which is a common emitter with a common base. Okay. This is also a famous circuit. It's called the Cascode Amplifier. It has a weird name, but this is the name it's famous for. It's called the Cascode Amplifier. Okay. It should be also easy to analyze. I will give you hints in the homework how to do the analysis, okay, in order to get the solution. Well, thank you very much and have a great day. Bye-bye.